Hello everyone, this video series is about vaccines. So this is the first video of that vaccine series. Vaccine series in the sense some immunology related aspects of vaccines. So let's start. First I would like to say that I'm a beginner and I don't know anything about this topic. I'm a beginner. So together we can learn about vaccines, some immunology related aspects. So come let's explore this topic with me. The discipline of immunology has its roots in the early vaccination trials of Edward Jenner and Louis Pasteur. Since those pioneering efforts, vaccines have been developed for many diseases that were once major afflictions of mankind. The incidence of diseases such as diphtheria, measles, mumps, pertussis, that means whooping cough, rubella, German measles, poliomyelitis, and tetanus has declined dramatically as vaccination has become more common. Clearly, vaccination is a cost effective weapon for disease prevention. Perhaps in no other case have the benefits of vaccination been as dramatically evident as in the eradication of smallpox, one of the mankind's long standing and most terrible scourges. Since October 1977, not a single naturally occurred smallpox case has been reported anywhere in the world. Equally encouraging is the predicted eradication of polio through large scale vaccination programs. This program had a serious setback caused by suspension of vaccination in Nigeria and in some areas of India and Pakistan. These countries, as well as others to which the disease spread, notably Yemen and Indonesia, witnessed outbreaks of paralytic polio following this cessation of immunization. Fortunately, the program is again underway, and the introduction of a new monovalent vaccine that produces immunity against a single strain has shown efficacy in regions where only that strain of polio circulates. So, a new addition to the weapons against childhood disease is a vaccine against bacterial pneumonia, a major cause of infant death. A crying need remains for vaccines against other diseases. Every year, millions throughout the world die from malaria, tuberculosis, and AIDS, diseases for which there are no effective vaccines. It is estimated by the World Health Organization that 14,000 individuals a day become infected with HIV-1 and the virus that causes AIDS. An effective vaccine could have an immense impact on the control of this tragic spread of death and disaster. In addition to the challenges presented by diseases for which no vaccines exist, the need remains to improve the safety and efficacy of present vaccines and to find ways to lower their cost and deliver them efficiently to all who need them, especially in developing countries of the world. WHO estimated that millions of infant deaths in the world are due to diseases that could be prevented by existing vaccines. So, that is how vaccines are important. The road to successful development of a safe and effective vaccine that can be approved for human use, manufactured at reasonable cost, and efficiently delivered to at risk populations is long, costly, and tedious. So, procedures for manufacture of materials that can be given to humans are tightly regulated, as are the protocols for testing these materials in clinical trials. Even those candidate vaccines that survive initial scrutiny and are approved for use in human trials are not guaranteed to find their way into common usage. Experience has shown that not every vaccine candidate that was successful in laboratory and animal studies prevents disease in humans. Some potential vaccines cause unacceptable side effects, and some may even worsen the disease they were meant to prevent. Live virus vaccines pose a special threat to those with primary or acquired immunodeficiency. Stringent testing is an absolute necessity because approved vaccines will be given to large numbers of people. Adverse side effects, even those that occur at very low frequency, must be balanced against the potential benefit of protection by the vaccine. Vaccine development begins with basic research. Recent advances in immunology and molecular biology have led to effective new vaccines and to promising strategies for finding new vaccine candidates. Knowledge of the differences in epitopes recognized by T cells and B cells has enabled immunologists to begin to design vaccine candidates to maximize activation of both cellular and humoral immune responses. So, as differences in antigen processing pathways become evident, scientists began to design vaccines and to use adjuvants that activate innate immune responses or processes and maximize antigen presentation with class 1 or class 2 MHC molecules. Genetic engineering techniques can be used to develop vaccines to maximize the immune response to selected epitopes and to specify delivery of the vaccines. In this chapter, we describe the vaccines now in use and describe vaccine strategies, including experimental results that may lead to the vaccines of the future. So, this session will only focus on some basic concepts like active and passive immunization, some related topics like that. So, let's start. Active and passive immunization. Immunity to infectious microorganisms can be achieved by active or passive immunization. In each case, immunity can be acquired either by natural process, usually by transfer from mother or to fetus, or by previous infection by the organism, or by artificial means such as injection of antibodies or vaccines. The agents used for inducing passive immunity includes antibodies from humans or animals, whereas active immunization is achieved by inoculation with pathogens that induce immunity but do not cause disease, or with antigenic components from the pathogens. In this section, we describe current usage of passive and active immunization techniques. First, passive immunization involves transfer of preformed antibodies. Edward Jenner and Louis Pasteur are recognized as the pioneers of vaccination or induction of active immunity, but similar recognition is due to Emil von Behring and Hidesborough Kitasato. I'm not sure what the pronunciation of these two names, sorry, for their contribution to passive immunity. These investigators were the first to show their immunity elicited in one animal can be transferred to another by injecting it with serum from the first. Passive immunization, in which performed antibodies are transferred to a recipient, occurs naturally by transfer of maternal antibodies across the placenta to the developing fetus. Maternal antibodies to diphtheria, tetanus, streptococci, rubella, mumps, and poliovirus all afford passively acquired protection to the developing fetus. Maternal antibodies present in colostrum and milk also provide passive immunity to the infant. Passive immunization can also be achieved by injecting a recipient with preformed antibodies. In the past, before vaccines and antibodies become available, passive immunization provided a major defense against various infectious diseases. Despite the risks incurred by injecting animal serum, usually horse serum, this was the only effective therapy for otherwise fatal diseases. Currently, several conditions warrant the use of passive immunization, including the following: deficiency in synthesis of antibody as a result of congenital or acquired B cell defects alone or together with other immunodeficiencies; exposure or likely exposure to a disease that will cause complications. So, first, deficiency in synthesis of antibody as a result of congenital or acquired B cell defects alone or together with other immunodeficiencies. Then, exposure or likely exposure to a disease that will cause complications. A child with leukemia exposed to varicella or measles, or when time does not permit adequate protection by active immunization. Then, infection by pathogens whose effects may be ameliorated by antibody. For example, if individuals who have not received up-to-date active immunization against tetanus suffer a puncture wound, they are given an injection of horse antiserum to tetanus toxin. The preformed horse antibody neutralizes any tetanus toxin produced by Clostridium tetani in the wound. So, passive immunization is routinely administered to individuals exposed to botulism, tetanus, diphtheria, hepatitis, measles, and rabies, and it can provide immediate protection to travelers or healthcare workers who will soon be exposed to an infectious organism and lack active immunity to it. Passively administered antiserum is also used to provide protection from poisonous snake and insect bites. Because passive immunization does not activate the immune system, it generates no memory response and the protection provided is transient. For certain diseases such as the acute respiratory failure in children caused by respiratory syncytial virus (RSV), passive immunization is the best preventative currently available. A monoclonal antibody or a combination of two monoclonal antibodies may be administered to children at risk for RSV disease. These monoclonal antibodies are prepared in mice but have been humanized by splicing the constant regions of human IgG to the mouse variable regions. This modification prevents many of the complications that may follow a second injection of the complete mouse antibody, which is a highly immunogenic foreign protein. So, although passive immunization may be an effective treatment, it should be used with caution because certain risks are associated with the injection of preformed antibody. If the antibody was produced in another species, such as horse, the recipient can mount a strong response to the isotypic determinants of the foreign antibody. This anti-isotype response can cause serious complications. Some individuals, for example, produce IgE antibody specific for determinants on the injected antibody. Immune complexes of these IgE bound to the passively administered antibody can mediate systemic mast cell degranulation, leading to systemic anaphylaxis. Other individuals produce IgG or IgM antibody specific for the foreign antibody, which form complement activating immune complexes. The deposition of these complexes in the tissues can lead to type 3 hypersensitivity reactions. Even when human gamma globulin is administered passively, the recipient can generate an anti-allotype response to the human immunoglobulin, although its intensity is usually much less than that of an anti-isotype response. An active immunization elicits long-term protection, whereas the aim of passive immunization is transient protection or elevation of an existing condition. The goal of active immunization is to elicit protective immunity and immunologic memory. An active immunization is successful as subsequent exposure to the pathogenic agent elicits a highlighted immune response that successfully eliminates the pathogen or prevents disease mediated by its products. Active immunization can be achieved by natural infection with a microorganism, or it can be acquired artificially by administration of a vaccine. In active immunization, as the name implies, the immune system plays an active role. Proliferation of antigen reactive T and B cells result in the formation of memory cells. Active immunization with various types of vaccines has played an important role in the reduction of deaths from infectious diseases, especially among children. So, vaccination of children is begin at about 2 months of age. Recommended program of childhood immunization in this country, updated in 2006 by the American Academy of Pediatrics. This country in the sense, I guess, America, because the book which I'm reading is kind of related to that country. QB. Hepatitis B vaccine, diphtheria, pertussis, cellular tetanus combined vaccine, Haemophilus influenzae vaccine, activated Salk polio vaccine, IPV. The oral Sabin vaccine is no longer recommended for use in the United States. Measles, mumps, rubella combined vaccine, varicella zoster vaccine for chickenpox, meningococcal vaccine recommended at 24 months for high-risk groups, at 11 to 12 years for all children. Pneumococcal conjunct vaccine (PCV), influenza vaccine now recommended for children 6 to 23 months old. Then hepatitis A vaccine. Hepatitis A vaccine is now recommended for all children between 12 and 23 months of age. Previously, it was given only to infants in high-risk populations. Similarly, influenza vaccines were formerly recommended for children with certain risk factors such as asthma or immunodeficiencies, but annual vaccination is now recommended for healthy children based on the increased risk of children in this age group for influenza-related hospitalization. The new list of recommendations also includes an assessment of immunity against the major childhood diseases between 11 and 12 years of age and catch-up immunizations for those requiring them. So, the introduction and spreading use of various vaccines for childhood immunization has led to a dramatic decrease in the incidence of common childhood diseases for which vaccination is currently recommended in the United States. The comparisons of disease incidence in 2004 to that reported in the peak years show dramatic drops, and in two cases, complete elimination of the disease in the United States. As long as widespread effective immunization programs are maintained, the incidence of these childhood diseases should remain low. However, the occurrence of side reactions to a vaccine may cause a drop in its use, which can lead to re-emergence of that disease. For example, the side effects of the pertussis attenuated bacterial virus include seizures, encephalitis, brain damage, and even death. Decreased usage of the vaccine led to an increase in the incidence of whooping cough. So, the recent development of an acellular pertussis vaccine that is an effective as older vaccine but with none of the side effects is expected to reverse this trend. As indicated, children typically require multiple boosters, repeated inoculations at appropriately timed intervals to achieve effective immunity. In the first months of life, the reason for this may be persistence of circulating maternal antibodies in the young infant. For example, passively acquired maternal antibodies bind epitopes on the DPT vaccine and block adequate activation of the immune system. Therefore, this vaccine must be given several times after the maternal antibody has been cleared from an infant's circulation in order to achieve adequate immunity. So, passively acquired maternal antibody also interferes with the effectiveness of the measles vaccines. For this reason, the MMR vaccine is not given before 12 to 15 months of age. In third world countries, however, the measles vaccine is administered at 9 months, even though maternal antibodies are still present, because 30% to 50% of young children in these countries contract the disease before 15 months of age. Multiple immunization with the polio vaccine are required to ensure that an adequate immune response is generated to each of the three strains of poliovirus that make up the vaccine. So, recommendations for vaccinations of adults depends on the risk group. Vaccinations for meningitis, pneumonia, and influenza are often given to groups living in close quarters like military recruits and incoming college students, or to individuals with reduced immunity, in the sense the elderly person. And depending on their destination, international travelers are also routinely immunized against each endemic disease as cholera, yellow fever, plague, typhoid, hepatitis, meningitis, typhus, and polio. Immunization against the deadly disease anthrax has been reserved for workers coming into close contact with infected animals or producers products from them. Recently, however, suspected use of anthrax spores by terrorists or in biological warfare has widened use of the vaccine to military personnel and civilians in areas at risk of attack with this deadly agent. So that was brand new information for me, because anthrax spores are used as biological tools or just bombs. They are used in the biological warfare. Vaccination is not 100% effective. With any vaccine, a small percentage of recipients will respond poorly and therefore will not be adequately protected. This is not a serious problem if the majority of the population is immune to an infected agent. In this case, the chance of susceptible individual contacting an infected individual is so low that the susceptible one is not likely to become infected. This phenomenon is known as herd immunity, and you might have already learned about this because we are coming from a post-pandemic era, like COVID-19 was there. So after that, we are to a great extent familiar with this term of herd immunity. The appearance of measles epidemics among college students and unvaccinated preschool age children in the United States during the mid to late 1980s resulted partly from an overall decrease in vaccinations, which had lowered the herd immunity of the population. Among preschool age children, 88% of those who developed measles were unvaccinated. Most of the college students who contracted measles had been vaccinated as children, but only once. The failure of a single vaccination to protect them may have resulted from the presence of passively acquired maternal antibodies that reduced their overall response to the vaccine. The increase in the incidence of measles prompted the recommendation that children receive two immunizations with the combined measles, mumps, rubella vaccine, one at 12 to 15 months of age and second to 4 to 6 years. The Center for Disease Control (CDC) has called attention to the decline in vaccination rates and herd immunity among American children. For example, a 1995 publication reported that California, nearly one-third of all infants were unvaccinated, and about half of all children under the age 2 were behind schedule on their vaccination. And I would like to mention something. This book, is targeted to students of America, so that's why I'm mentioning about them. Sorry for that, because the book I'm following is, targeted to American children or students. So the targeted group, along with the sample collected, will also be related to American children. So that's why my data is always related to Americans, nothing else. Such a decrease in herd immunity portends serious consequences. By the mid-1990s, a diphtheria epidemic was raging in many regions of these new countries, linked to a decrease in herd immunity resulting from decreased vaccination rates after the breakup of the Soviet Union. This epidemic, which led to over 157,000 cases of diphtheria and 5,000 deaths, is now controlled by mass immunization programs. And designing vaccines for active immunization. The majority of infections are dealt with by non-specific or innate immune mechanisms, which include complement, interferons, NK cells, activated phagocytes, antimicrobial compounds, and other mechanisms. The adaptive immune response provides a more flexible resistance to pathogens. Vaccination educates the adaptive immune system, preparing it to deal effectively and swiftly with pathogens not readily eliminated by innate immunity. Several factors must be kept in mind in developing a successful vaccine. First, the development of a measurable immune response does not necessarily mean that a state of protective immunity has been achieved. Often critical is the branch of immune system that is activated, and therefore vaccine designers must recognize the important differences between activation of the humoral and cell-mediated branches. A second factor is the development of immunologic memory. For example, a vaccine that induces a protective primary response may fail to induce the formation of memory cells, leaving the host unprotected after the primary response to the vaccine subsides. The role of memory cells in immunity depends in part on the incubation period of the pathogen. In the case of influenza virus, which has a very short incubation period, 1 to 2 days, disease symptoms are already underway by the time memory cells are activated. So, effective protection against influenza, therefore, depends on maintaining high levels of neutralizing antibody by repeated immunizations. Those at highest risk are immunized each year. For pathogens with longer incubation period, maintaining detectable neutralizing antibody at the time of infection is not necessary. The poliovirus, for example, requires more than 3 days to begin to infect the central nervous system. An incubation period of this length gives the memory B cells time to respond by producing high levels of serum antibody. Thus, the vaccine for polio is designed to induce high levels of immunologic memory. After immunization with the Salk vaccine, serum antibody levels peak within 2 weeks and then decline, but the memory response continues to climb, reaching maximum levels of at 6 months and persisting for years. If an immunized individual is later exposed to the poliovirus, these memory cells will respond by differentiating into plasma cells that produce high levels of serum antibody, which defend the individual from the effects of the virus. In the remainder of this chapter, various approaches to the design of vaccines, both currently used vaccines and experimental ones, are described, with an examination of the ability of the vaccines to induce humoral and cell-mediated immunity and the production of memory cells. Common vaccine currently in use consist of live but attenuated organisms, inactivated or killed bacterial cells or viral particles, or protein or carbohydrate fragments, subunits of the target organisms. Under careful study are several new types of vaccine candidates that provide advantages in protection, production, or delivery to those in need. The primary characteristics and some advantages and disadvantages of the different types of vaccines are included in this listing. The following sections describe each of the vaccine types, indicating how they are currently used or how they must be best applied to human diseases. So that topic we will be including in the next video. So in that we will be learning some aspects related to the live attenuated vaccines, some topics related to the inactivated or killed vaccines along with subunit vaccines, toxoids used as vaccines, bacterial polysaccharide capsules, viral glycoproteins as candidate vaccines, pathogen proteins, then synthetic peptides as vaccines, along with conjugate vaccines, recombinant vector vaccines, and DNA vaccines. This is going to be a long session. So today we are going to stop here. Tomorrow we will be learning other aspects. Thank you for listening.